All right, let's get started. So, today we have reached the point where we are going to move from the traditional AI to modern AI. We are going to do a completely different kind of AI starting this class. And we will continue the language of knowledge representation, right, the theme of knowledge representation that we have been working on. So, now let us go back to what AI have we been doing. We have said that look, state is very important in AI, because state models the world, state models the problem situation, and then we can use that state as a fundamental unit to move in the search space and so on and so forth. Okay. And then at some point we said look, state can't be indivisible, there are properties in a state, we need to somehow expose those properties in a state. Moreover, in any problem there is some knowledge that the machine must have, and that knowledge needs to be encoded one way or the other. And on the basis of that, if we encode such a knowledge, the machine might be able to have some more inferences and so on and so forth. So, then we started talking about some languages, and we talked about constraint satisfaction as one of the languages where we have variables and values, and that becomes part of the state. And then we talked about propositional logic, where we are modeling facts and we always know what is the fact true or is the fact false. And if we do not know whether the fact is true or the fact is false, we say that I do not know the value of that particular fact and so on, right. And then there is something called first order logic, where we have relations and objects, and facts are formed on the basis of relations applied on objects, and again we know that whether that particular fact is true, false or unknown, right. And there are many different kinds of logics, as we have earlier discussed, like there may be temporal logic where we add notion of time. There may be fuzzy logic where we say that my fact itself may not be true or false, my fact itself may not represent something that is always true or false, it may represent something that is fuzzy, the truth itself is fuzzy, right, and we may know it and we may not know it, right. And then we said that there is another way of thinking about life, which is probabilistic. And in a probabilistic worldview, we are still modeling facts, just like propositional logic. So, it is not as if the commitment on what we are capturing in terms of symbols and so on and so forth, that has changed significantly. What has changed is what we know about it, right. So, a fact may be true, the fact may be false, but when we do not know a fact, we do not say we just do not know it, we do not say that it is just unknown, we additionally attribute some probability, some degree of belief. So, when we do not know it, we say that I do not know it, but I believe it to be true with the probability 0.9 or 0.1 or 0.5, and that allows us to do more fine grained reasoning, more fine grained inference, and as we shall see, that became the basis of the modern AI, and that is very important. So, but I will also point out that like we have a first order logic which has facts, objects and relations with true false. We also have first order probabilistic models, also called probabilistic relational models, also called statistical relational learning, which combine probability and first order logic. And in the whole of late 90s and early 2000s, this was the rage in AI, or a rage in AI. There was so much work that was going on in combining first order logic and probabilistic models. However, we would not go there. Actually, I would say that jury is still out, that in the modern deep learning world, whether that is still as important as it was considered it to be 10 years ago, and we do not know the answer to that, only time will tell, right. Now, the next thing I would say is that reasoning with uncertainty is incredibly important. As I was saying, that this became the basis of modern AI. And the first thing you have to realize is the world actually is full of uncertainty. Now, this is a complicated question. Is the world really full of uncertainty? Like when I toss the coin, I say that with probability half I am going to get heads and with probability half am I going to get tails. Is it really what that is happening? Is it a probabilistic outcome in the real world? How many of you believe that this is really a probabilistic outcome? Nobody believes there is really a probabilistic outcome. 1%, 3 people, please raise your hands, come on. And how many people believe that it is actually a deterministic process? right. So, you can see many more people feel that my tossing the coin is actually a deterministic process. Of course, they know that I do not know what the answer is going to be, but if we could model all the physics if we could model the exact coin, if we could model the exact impulse that I give, the exact angle at which I give the impulse, the exact height from the ground where I toss the coin, the exact molecules in the air, etc., 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 some people may believe that we would exactly be able to predict what the outcome is. So, people may believe that the world is actually deterministic, but is the world really deterministic? Why not? Quantum, right? So, then when we go to subatomic level, then we may start to believe, oh, it's Schrodinger, we do not know whether the cat is alive or dead, and the world is actually probabilistic. So, now what I have done for you is that I have started from a world where we said that it is probabilistic, then said no, the world is actually deterministic, and then said no, the world is actually probabilistic. Now, which of these is the truth? Is a very hard question, right? And you can philosophize about it, that is up to you. The main point I want to raise here is that depending upon the abstraction at which we model the world, we may or may not be able to capture the determinism in it, even if it were present. Like, for example, let us believe that the coin tossing is a deterministic event. The amount of modeling I need to do, the exact air molecules, the exact impulse, the exact this and the exact that, it is just not going to be feasible to practically model all this. What might be easy to say is that I am not going to model any of it. I will simply say you toss a coin and with probability 0.5 you get heads and with probability 0.5 you get tails. That is it. Yes, Parth. Why are we saying that with probability 0.5 we get heads and probability 0.5 we get tails? Because we are assuming that the coin is fair, and if we do a million trials, then with a very, very high chance you will have a more relatively even distribution. There is no bias on one side or the other. That is what we are saying. So, this leads us to the very famous saying, very famous quotation, that all models are wrong. I have said this before. Some are okay. So, that is not the saying. Where you can make your saying that all models are wrong, some are less wrong. That is not technically invalid as a saying. Now, it is a saying, it is the AI class of IIT Delhi is saying, but the famous saying is that all models are wrong, some are useful, right. And so, you often ask the question, how much do I model? Do I model all the complexity of the world? And sometimes all the little complexity is very hard to take care of, because you do not have enough data to learn for it, there are so many corner cases and exceptions and you can't enumerate all of them and so on and so forth. And therefore, and I will come back to it again in the next class, therefore, we abstract it out. We say that we will model the world at some level of abstraction and put all these corner cases in some randomization or some probability distribution. And this is exactly why we say coin is 0.5 heads, 0.5 tails, right. Moreover, what I would show you later is that logic is brittle. It is not easily possible to encode exceptions to rules. It is definitely not possible to encode statistical properties in a domain. And because of all of this, and probability became a new foundation for AI, and some people believe also for computer science. Right? Oh, by the way, the world itself is full of uncertainty. If I have a real robot, there is sensor noise, it is trying to say that the obstacle is 4 feet away, but there is some randomness and some uncertainty there, etc., 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 right. Many kinds of uncertainties. We have talked about expecting minimax, that is an uncertainty in the chance node, what happens, this happens or that happens. There is sensor noise, which is reading uncertainty. There is actuator error. I tried to move my hand 4 feet, but it only moved 3.95 feet, right. This is possible. That will be error in the motor rotation and so on and so forth. I may not even know all the information. So, there is uncertainty in what I do not know. Like, I do not know where Kashika is today, right. She is somewhere, but she is not here today. So, I do not know where she is, right. So, the point is that is partial information. We do not exactly know everything in the world, and so because of all of this partial information, reading and observation information and uncertainty, action uncertainty, etc., we have to deal with it one way or the other, right. The other reason uncertainty becomes critical is that data has become very central in the field of AI. And when you later do a machine learning course, the whole of the class will be about, how do I use data and train a model, right. So, massive amounts of data today, statistics and computer science are both about data now, right. Statistics obviously is, it lets us summarize and understand it, it is the basis therefore for most learning, because when we learn from data, we cannot say deterministic things, we cannot be sure about everything. We can only make probabilistic statements, because it is possible that there is some data we have never seen before, right. And so, because of that, we need to somehow capture probability, right. So, there are many reasons why probabilistic AI has more real world implications than the pure logic based AI. And in this class today, we will just quickly go over the very basics of probability, which you should already know, right. We will maybe introduce one important concept, but other than that it is going to be old revision. So, I am going to go through this fast, but if you have questions, please stop. Okay. So, in logic we have symbols, in probability we have random variables. Okay. Random variables are what? Are the units of probability. Symbols can take values true and false, random variables may not, they may take any value, like from a domain, heads and tails, or from a domain 1 to 6, or true false also. State of the world was always the complete assignment to all the variables, right. This is where the logic came into picture. We said you can go inside the state, there are many state variables, and these state variables take values true and false, and if I completely enumerate all the variables, then that is a state. In the very same way, probability folks use the word atomic event, it is the same thing as a state, there is no difference. Okay. It is again a complete specification of the world, complete assignments to all the random variables, right. And this complete assignment is called an atomic event, a set of atomic events if all these worlds are mutually exclusive, that means two worlds cannot co-occur, and exhaustive, like if I enumerate all the possible atomic events and states, then I am not missing anything. In addition, we will need 2 new or 3 new definitions of probability, which are very easy to understand. One is going to be prior probability distribution, one is going to be joint probability distribution, and later one is going to be posterior probability distribution. Okay. These 3 terms you will learn, these are very easy terms. For example, a prior probability of any random variable or any event, may not be an atomic event, any event, is just its unconditional probability. I am not given any information and I am saying what is the probability of a certain event, right. On the other hand, joint distribution is probability of a state, probability of a full specification of the atomic event, full atomic event. So, probability of an atomic event is called the joint distribution, and probability of any event without any additional information is called a prior probability. And again, if this does not get clear, we will give you more examples to make it clear. Okay. So, let us quickly look at some examples. So, let us say I always have a sample space. So, sample space is all the possibilities of a random variable. For example, there are 6 rolls of a die. So, the sample space would be 1, 2, 3, 4, 5, 6. An X would be a sample point, a possible world, an atomic event. A probability space or a probability model is a sample space with an assignment P of X for every X, such that each of Px is between 0 and 1 and sum over all Px is 1. I think that is obvious to you guys. An event is any subset of S. So, die roll less than 4 is an event, it is not an atomic event, but it is an event. And a random variable is a function from sample points like 1, 2, 3, 4, 5, 6 to some range, like range of reals or range of booleans. And so, if suppose I have a sample space of red, blue, green, then if we have a function that gives red the value 1, blue the value 2 and green the value 3, then that will be called a random variable. Okay. And now, your probability spaces may be propositional like boolean. For example, do I have a cavity in my teeth? We will be using Mr. Bean's dentist appointment as the running example today. So, I will demonstrate it in a few minutes. The random variables may be discrete, like is it sunny or rainy or cloudy or snowy. The random variables may be continuous. Is the temperature 21.6? Is it 22.0? Or if you are India, is the temperature 31.2 or 32.0? And these are continuous. They may be bounded, they may be unbounded, right? As the global warming is going on, it's sort of slowly looking like unbounded, but we shall see. Maybe it will not be unbounded because we will all die before the bound gets exceeded. That's also a possibility. That's a joke. So, looks like you are not following the class today since you didn't laugh, or I guess it's too serious of a joke for you to laugh. It is not clear whether you will live your whole life to see the earth at that level. I hopefully will live my life, who knows. So, you should think about how to use AI for global warming at some point, but you can't do that in the US because US does not believe in global warming. So, you have to do it in India or somewhere else, Germany maybe. Okay. Good, at least you laughed. So, you are here. Okay. So, and then we know this basic theorem which says probability of A or B, two events A or B is probability of A plus probability of B minus probability of A intersection B. I am pretty sure everybody knows this. Probability of A is sort of capturing this red space, probability of B is sort of capturing this blue space, but there is one common space that has been captured twice. So, you have to subtract it and so on. Okay. So, now this is what is prior probability, right. So, prior probability is also called the unconditional probability of any event, right. So, what is the probability that Mr. Bean has cavity? What is the probability that the weather is sunny in the month of September in Delhi, right. So, reasonable probability 0.72 seems reasonable. So, notice that prior probability corresponds to our belief prior to arrival of any new evidence. For example, in the case of Mr. Bean, suddenly he may observe that one of his tooth is sort of moving, or he may observe that he has toothache, and that new observation, that new evidence might change his distribution of whether he has cavity or not. Make sense? But suppose I do not give you this new evidence or any new evidence whatsoever, then what is the initial belief before you get any information of whether Mr. Bean has cavity or not? That is called the prior probability. Prior probability is the probability prior to seeing any evidence. Okay. Now, probability distribution is the probability of the whole distribution of all the possible events, atomic events and their values, like for weather. So, you may have a snowy weather, cloudy weather, rainy weather, sunny weather, and let us say the probability distribution would sum to 1 obviously, and that would be all the values will be called a distribution. Now, suppose I want to model two random variables in my domain, one is what is the weather, one is whether Mr. Bean has cavity or not. Then I can define a joint probability distribution. A joint probability distribution would be a set of random variables that give a probability for every atomic event on those random variables, right. So, for example, for probability weather comma cavity, I will have a 4 cross 2 matrix of values for each possible weather condition and each possible cavity condition. Okay. For example, this might look like the distribution. You may say that whether sunny and cavity true is 0.144, whether cloudy and cavity false is probability 0.064. Now, what is very interesting is that we will very soon show that joint distribution can answer every question that you may have about this probability distribution, and if it is not clear to you, it will get clear to you in a few slides from now. Okay. So, joint distribution is what we want. If we have the joint distribution, we have everything. Okay. But before that, we have to define conditional probability. Again, you know what is a conditional probability. It is also called the posterior probability. Prior probability was before seeing any evidence, posterior probability is posterior to seeing some evidence, right. So, it is the conditional probability conditioned on the evidence that you have seen. Like what is the probability of the cavity if I am given toothache, and that may be very high, because if you have toothache, there is a good chance you have cavity. Yes.
The previous slide,
question. So, when in the previous probability we had probability of weather, whether it is sunny and so on and so forth, can we call it the prior probability? Yes, any prior probabilities which is without giving any new evidence. So, when you are not giving any evidence, you will call it a prior probability. However, a prior probability which is giving a value for all possible random variables, the full state, is also called the joint probability. Okay. And notice that probability of cavity given toothache is a 2 element vector of 2 element vectors, because toothache may be true or false, and for that cavity may be true or false. So, that is a, for toothache true I have 2 values, for toothache false I have 2 values. Of course, those values independently, given toothache is true, probability of cavity and probability of not cavity sums to 1, sum to 1. So, when they sum to 1, I can get away by only keeping one value, because I can use this to compute the other value. Okay. And now, one of the most interesting things that is going to happen in our world, and we will talk more about this very soon, is that new evidence may be irrelevant. By knowing the new evidence, I do not get any new information about the probability that I am interested in. For example, probability of cavity given toothache and that weather is sunny will be equal to probability of cavity given toothache, because sunny is irrelevant unless it remains sunny so much, and it is so sunny that because of that the microbes increase, and because the microbes increase there is cavity, and because the cavity there is toothache. It is possible, but again remember, it's which level do we model the problem, right? So, you can say that probability that path has cavity given that Arsh does not have cavity. Now, you could say that, oh, these are two independent things. By knowing whether Arsh has cavity or not, I do not get any new information about path, and so I will say that probability path has cavity given Arsh has cavity is equal to probability path has cavity. On the other hand, you could say, oh, one person has cavity, maybe because they live in the same world, more people have cavities. By knowing one person has cavity, we increase the overall probability distribution that people here have cavities, therefore, we increase the probability that path has cavity. There is nothing wrong in this logic per se, but is it something we want to model, or is it not something we want to model? And so, if we are not modeling this kind of behavior and phenomenon, because we say that the influence is very weak, then we will just say that they are sort of new evidence does not matter, and the technical term we use for this is that the two variables are independent, and we will see more about this in a minute. And by the way, this kind of inference is the most important inference for probabilistic modeling, and we shall see that too. Okay, so let us get into it. Oh no, we quickly have to define conditional probability pictorially. So, A given B is A intersection B, which is the common area, divided by probability of B, which is the blue area. Why? Because given B, we are only interested in the blue part, nothing else matters. And then last but not the least, this is chain rule. Everybody knows the chain rule, and chain rule is most important. Probability of a joint distribution is in any order start with prior probability of x1 times probability of x2 given x1 times probability of x3 given x1 comma x2, and so on, times probability of xn given all the other n minus 1 variables. This is always true. This does not require any additional knowledge about the variables in any order. This is called the chain rule or the product rule. Okay. So, at this point we have quickly covered everything that you already know about probability distributions.